The earliest epochs of planetary history are written in silence, yet their consequences echo across billions of years. Within the first 100 million years, the architecture of a planetary system is largely determined. Mass accumulates where it can, orbits stabilize where they must. What remains afterward is evolution, slow, relentless transformation guided by energy flow and internal dynamics. A planet's initial composition sets the stage, but time directs the performance. Energy is the driver of planetary change. It arrives primarily from two sources: stellar radiation and internal heat. Radiation shapes climates, powers atmospheric circulation, and fuels photochemical reactions. Internal heat drives volcanism, tectonics, and magnetic dynamos. When either source diminishes, planetary activity slows. When either source intensifies, instability may result. The balance between incoming and outgoing energy defines whether a world freezes, burns, or maintains equilibrium. On rocky planets, crust formation marks a turning point. Once a solid surface stabilizes, impacts leave lasting marks. Volcanic plains spread and cool. Mountain ranges rise where crust compresses. Rift valleys open where crust stretches thin. These features record stress patterns generated by internal convection and external gravitational forces. Over time, erosion reshapes them. Wind sculpts rock, water carves valleys, ice grinds mountains into sediment. Planetary surfaces are canvases upon which physics paints continuously. Sedimentation becomes a chronicle of planetary climate. Layer upon layer of material accumulates in basins, preserving chemical signatures of atmospheric composition and environmental conditions. On Earth, sedimentary rocks reveal shifts from oxygen-poor atmospheres to oxygen-rich ones. They record glaciations, warming events, and biological revolutions. If similar records exist on other worlds, they remain locked beneath alien landscapes, waiting for exploration. Atmospheric chemistry evolves in response to geological and possibly biological influences. On Earth, early atmospheres contained little free oxygen. Only after photosynthetic organisms began releasing oxygen did atmospheric composition transform dramatically. Oxygen reacted with surface minerals, altering rock chemistry and enabling new forms of metabolism. This transformation demonstrates how planetary evolution can be driven not only by physical forces but by life itself. Whether such biological feedbacks occur elsewhere remains unknown, yet the possibility reshapes the search for habitable worlds. Cloud formation influences planetary albedo and temperature. High reflective clouds cool surfaces by deflecting sunlight. Thick greenhouse atmospheres trap infrared radiation, warming surfaces below. Atmospheric circulation redistributes heat from equator to poles. On rapidly rotating planets, jet streams form. On slowly rotating planets, circulation cells may span entire hemispheres. The complexity of climate systems arises from fluid dynamics interacting with rotation, gravity, and energy input. In giant planets, atmospheric bands reveal powerful winds flowing at hundreds of meters per second. Storm systems can persist for centuries, driven by internal heat rising from below. Deep convection transports energy outward, creating layered cloud decks composed of ammonia, water, and other compounds. Lightning flashes within these turbulent clouds. Though lacking solid surfaces, these planets are dynamic, alive with motion. Moons expand the diversity of planetary systems. Some are captured asteroids, others formed alongside their parent planets within circumplanetary disks. Large moons can rival planets in complexity. Tidal interactions between a moon and its planet can lead to synchronous rotation, where one face permanently points toward its host. These interactions dissipate energy as heat, altering internal structures. In certain cases, tidal heating may sustain liquid oceans beneath icy crusts for billions of years, creating environments shielded from harsh surface radiation. The geometry of planetary systems determines stability. Systems with closely spaced massive planets may experience long-term instabilities, eventually leading to collisions or ejections. Others achieve resonant configurations that maintain order. Observations of exoplanet systems show chains of resonant planets orbiting in precise ratios, indicating migration during formation. These resonances serve as fossils of early disk interactions. Dust grains, the smallest building blocks of planets, originate in stellar atmospheres and supernova explosions. Carbon, silicon, iron, each atom forged in nuclear reactions deep within stars. When those stars died, they expelled enriched material into space. Subsequent generations of stars inherited that material. Planet formation is thus a recycling process, assembling matter shaped by earlier cosmic events. Every rocky surface, every metallic core, every atmospheric molecule traces ancestry to stellar furnaces. As planetary systems age, smaller bodies continue to interact gravitationally. Comets from distant reservoirs occasionally plunge inward, bringing volatile compounds. Asteroids may collide with moons or planets, altering surfaces. Over time, the rate of such events declines, but never reaches zero. The risk of impact remains a constant background feature of planetary existence. Planetary rings demonstrate that not all debris consolidates into moons. Within certain orbital distances, tidal forces prevent accretion, shredding larger bodies into smaller fragments. These fragments spread into flattened rings, shaped by gravitational shepherds and resonances. Over millions of years, ring systems may disperse, coalesce into moons, or fall into their host planets. Even these elegant structures are temporary phases in longer evolutionary arcs. The measurement of planetary masses and radii reveals internal composition. A planet slightly larger than Earth but significantly more massive likely contains a dense iron core. A planet similar in size but lighter in mass may possess a thick atmosphere. Such distinctions inform theories about atmospheric retention and loss. Observations reveal that planets between Earth and Neptune in size are common throughout the galaxy, suggesting that intermediate classes may represent typical outcomes of formation. Some planetary systems form around low-mass red dwarf stars, which are abundant in the galaxy. Their habitable zones lie close to the star, increasing the likelihood of tidal locking. Yet these stars can be volatile, emitting flares that bathe nearby planets in radiation. Whether atmospheres can endure such conditions remains an active area of research. The resilience of atmospheres under stellar activity influences the potential for life. In star clusters, planets may form in crowded environments where nearby stars illuminate the disk or perturb orbits. External radiation can strip gas from protoplanetary disks, limiting giant planet formation. Thus, the birth environment influences planetary outcomes. Solitary stars like the Sun may provide more stable conditions for disk longevity, yet clusters remain common birthplaces for stars. The gravitational collapse that initiates star formation also sets angular momentum constraints. Because angular momentum must be conserved, collapsing clouds spin faster as they contract. Without mechanisms to redistribute angular momentum, collapse would halt prematurely. Magnetic fields and outflows help transfer angular momentum outward, allowing central stars and surrounding disks to form. These early processes indirectly determine how material spreads through the disk and where planets can accrete efficiently. Observations of young stellar objects reveal gaps within disk regions where forming planets have cleared paths. These gaps confirm that planet formation begins early, even while gas remains abundant. Disk lifetimes, typically a few million years, impose strict time limits. Gas giants must form quickly before gas dissipates. Rocky planets can continue accreting longer, assembling from leftover planetesimals after gas dispersal. As internal heat dissipates over billions of years, Geological activity declines. Smaller planets cool more rapidly due to higher surface area to volume ratios. This cooling influences volcanic activity and magnetic field generation. The cessation of a magnetic dynamo may expose atmospheres to erosion. The interplay between cooling rate and atmospheric retention shapes long-term habitability. Surface gravity influences atmospheric thickness. More massive planets retain thicker atmospheres, yet excessive mass may lead to crushing pressures and deep hydrogen envelopes unsuitable for surface oceans. There exists a delicate mass range in which rocky planets can support stable, temperate atmospheres. Observations suggest that many stars host planets within this size range, though confirming surface conditions remains challenging. Light from distant planets carries encoded information. During transits, certain wavelengths are absorbed by atmospheric gases, imprinting spectral lines upon starlight. By analyzing these patterns, scientists infer molecular presence. Future instruments aim to detect subtle combinations of gases that may indicate biological processes. The identification of such biosignatures would transform our understanding of planetary evolution. Planetary albedo varies widely. Bright clouds, ice caps, and reflective surfaces increase albedo, cooling a planet. Dark oceans or basaltic plains absorb energy, warming surfaces. Seasonal cycles alter albedo as snow and ice expand or retreat. Over long time scales, shifts in atmospheric composition can change cloud formation patterns, amplifying climatic transitions. The concept of equilibrium temperature provides a baseline for estimating planetary climates, yet real conditions depend heavily on atmospheric composition. A planet at Earth's distance from the Sun without greenhouse gases would be frozen. A planet slightly farther away with a thick greenhouse atmosphere might remain warm. Thus, simple distance from a star cannot alone determine habitability. As stars evolve off the main sequence, their expanding envelopes may engulf close-in planets. Some planets may spiral inward due to tidal interactions before stellar expansion. Others may survive in outer orbits, experiencing brief warming during red giant phases. When a star sheds its outer layers and becomes a white dwarf, surviving planetary remnants may continue orbiting the dense stellar core. In the far future, gravitational interactions between stars in the galaxy may disrupt planetary systems. Over trillions of years, stellar encounters could gradually unbind planets from their stars. Cosmic time extends far beyond the lifespans of individual systems. Planetary formation is therefore one chapter in an even longer cosmic narrative. The study of planetary origins unites multiple scientific disciplines: astrophysics, geology, chemistry, atmospheric science, and biology. Each contributes insights into how matter organizes itself into complex structures. The same physical constants operate everywhere: gravity, electromagnetism, thermodynamics. These forces shape dust into worlds. When we examine a rocky cliff on Earth or observe a distant exoplanet transit, we are witnessing different expressions of the same cosmic process. The atoms composing mountains were once scattered in space. The iron in Earth's core once resided in the heart of an ancient star. Through collapse, collision, heating, and cooling, those atoms assembled into a planet capable of sustaining oceans and life. Planetary formation is not a singular event but a continuum. It begins with diffuse gas and ends, perhaps, with conscious beings contemplating their origins. The transformation from dust to thought spans billions of years, yet it follows comprehensible physical laws. In understanding how planets form, we understand how environments capable of reflection and inquiry arise. Across the galaxy, countless stars shine upon their own systems of worlds. Some systems may resemble ours, many will not. Some planets will orbit alone, others will share complex gravitational dances. Some will harbor thick atmospheres of hydrogen, others will be barren rock. Yet all began within cold clouds where gravity slowly gathered matter. From that gathering came disks. From disks came planetesimals. From planetesimals came worlds. From worlds came climates. oceans, magnetic fields, storms, and perhaps life. The story begins in darkness and continues in light. Segment 1 ends not with completion but with continuity. Planetary formation set the stage billions of years ago, yet its consequences unfold still. Every orbit, every sunrise, every shifting tectonic plate is a reminder that planets are not static monuments but evolving systems shaped by ancient forces. From dust suspended in interstellar space to stable spheres tracing paths around stars, the birth of planets is a testament to gravity's quiet persistence. It is the story of matter assembling into structure, of chaos yielding to order, of time sculpting possibility. And in that vast unfolding, one small planet became home, a world forged in fire, tempered by water, shielded by magnetism, illuminated by a steady star. Its origins are not unique in mechanism, only in outcome as far as we know. The same processes operate everywhere. The universe is a factory of worlds. The birth of planets is the beginning of every planetary story. What follows, climate, geology, chemistry, biology, rests upon that foundation. To understand planets is to trace the path from gravity to complexity, from collision to calm, from molten beginnings to enduring orbits. This is how worlds begin. Beyond our solar system, terrestrial planets find analogues among exoplanets, revealing the diversity of rocky worlds. Observations of planets orbiting distant stars show sizes, densities, and orbital parameters similar to Mercury, Venus, Earth, and Mars, suggesting that the processes shaping rocky worlds are universal. Hot rocky exoplanets close to their stars may resemble Mercury, baked by stellar radiation and stripped of volatiles. Slightly more distant planets with thick atmospheres could mirror Venus, trapped in runaway greenhouse states. Planets within temperate zones may parallel Earth, maintaining liquid water and moderate climates. Those near the outer edges may resemble Mars, cold and thin-atmosphered, possibly capable of transient or subsurface liquid water. These analogues provide a framework for understanding how small variations in initial conditions produce radically different planetary outcomes. Stellar type influences the evolution of terrestrial exoplanets. Red dwarfs, the most common stars in the galaxy, emit lower luminosities but often produce flares and high-energy radiation. Planets in their habitable zones are typically close in, increasing tidal interactions that may result in synchronous rotation, where one side permanently faces the star. Such tidal locking can create extreme temperature contrasts between day and night hemispheres. Yet, atmospheric and oceanic circulation could mitigate these effects, redistributing heat. Stars like our Sun produce long-lived stable conditions, allowing rocky planets more time to develop complex geologies and climates. Stellar evolution therefore shapes the long-term prospects for habitability. Planetary atmospheres are shaped by a balance between accumulation, retention, and loss. Outgassing from volcanic activity adds gases to the atmosphere, while impacts can deliver or remove volatile compounds. Stellar wind and radiation strip atmospheres, particularly from smaller planets lacking magnetic protection. The size, mass, and distance from the host star determine whether a planet retains a dense atmosphere capable of moderating temperature and sustaining surface liquids. Mercury, Venus, Earth, and Mars provide natural experiments for these processes, offering insight into atmospheric evolution on exoplanets. Tectonic activity can influence climate regulation on terrestrial exoplanets. Plate tectonics facilitates the cycling of carbon between the crust, mantle, and atmosphere, stabilizing surface temperatures over geological timescales. Planets lacking tectonics may experience volatile extremes, runaway greenhouse heating, or irreversible cooling. Venus, without active plates, demonstrates the consequences of a stagnant lithosphere, whereas Earth benefits from continuous recycling and moderation. Exoplanets with varying sizes and compositions may occupy similar tectonic regimes, dictating their surface and atmospheric evolution. Volcanism contributes to the replenishment and composition of atmospheres. On Earth, volcanic eruptions release carbon dioxide, water vapor, and other gases critical for climate and life. Venus's massive volcanic plains suggest episodic gas release sufficient to sustain a dense atmosphere. Mars, smaller and cooler, experiences reduced volcanic activity, limiting atmospheric replenishment. Exoplanet analogues may display similar patterns, with volcanism acting as both a geological sculptor and an atmospheric regulator. Water plays a central role in shaping planetary habitability. Its presence or absence influences surface erosion, mineral formation, tectonic lubrication, and climate feedbacks. Planets with abundant surface water can moderate temperature extremes and support chemical cycles that stabilize climate. Water scarcity or loss, as on Mars and Venus, alters erosion, reduces weathering, and diminishes potential habitability. Exoplanet studies often focus on identifying liquid water, either on the surface or in subsurface reservoirs, as a key indicator of habitability. Magnetic fields shield planets from stellar radiation, protecting atmospheres and, potentially, life. Earth's magnetic field arises from convection in its liquid iron outer core, deflecting solar wind and cosmic radiation. Mercury's weak field provides partial shielding, while Mars, lacking a global field, lost much of its atmosphere. Venus's dense atmosphere compensates partially for the absence of a field. Exoplanetary magnetic fields, influenced by size, rotation, and interior composition, play similar roles in atmospheric retention and climate stability. Rotation and axial tilt influence climate patterns, heat distribution, and weather dynamics. Rapidly rotating planets like Earth develop Coriolis forces that shape atmospheric circulation and generate jet streams. Tidally locked planets around red dwarfs may experience extreme day-night temperature contrasts, but atmospheric circulation could redistribute heat. Seasonal variations from axial tilt produce climate fluctuations, influencing polar ice caps, desert regions, and precipitation cycles. Understanding rotation and tilt is essential for predicting climate regimes on terrestrial exoplanets. Impact cratering continues to shape planetary surfaces. Large collisions can create basins, redistribute crustal material, and trigger atmospheric loss. Mercury's heavily cratered surface preserves billions of years of impacts. Mars's southern highlands are densely cratered, while younger northern plains show reduced cratering. Earth's active geology erases most craters, though some, like Chicxulub, remain as reminders of catastrophic events. Exoplanets may experience similar impact histories, particularly in dense stellar environments or young systems with abundant planetesimals. Surface geology preserves the narrative of planetary evolution. On Mercury, scarps and craters record contraction and bombardment. Venus's volcanic plains reveal mantle upwelling and episodic resurfacing. Earth's mountains, rift valleys, and sedimentary layers record tectonics, erosion, and climate cycles. Mars's shield volcanoes, canyons, and dried riverbeds record mantle plumes, erosion, and water history. Exoplanet analogues likely exhibit similar patterns, shaped by gravity, internal heat, and surface composition. Climate feedback loops determine long-term planetary conditions. On Earth, the carbon cycle regulates temperature, preventing runaway extremes. Venus demonstrates positive feedback loops that trap heat, producing extreme greenhouse conditions. Mars illustrates how atmospheric loss and cooling produce irreversible decline. Exoplanets may experience similar feedbacks, with minor differences in composition, distance, or stellar radiation producing divergent climate trajectories. Habitability is the product of multiple converging factors: mass, composition, distance from the star, rotation, axial tilt, tectonics, volcanism, water presence, magnetic field, and atmospheric retention. Small variations in these parameters can produce dramatically different outcomes. Mercury, Venus, Earth, and Mars exemplify this principle, providing a blueprint for evaluating the potential of rocky exoplanets to sustain life. Comparative planetology allows scientists to infer unobservable properties of distant worlds. By studying interior dynamics, surface geology, atmosphere, and magnetic fields of solar system planets, researchers predict the conditions of exoplanets detected via transit, radial velocity, or direct imaging methods. Densities derived from mass and radius measurements indicate composition, while orbital characteristics suggest climate regimes and tidal influences. Surface conditions, though difficult to observe directly, can be inferred by analogy. Planetary evolution is a continuum rather than discrete events. Formation, differentiation, volcanism, tectonics, erosion, impact history, and atmospheric evolution proceed over billions of years. Each terrestrial world represents a unique trajectory shaped by initial conditions, stochastic events, and internal feedbacks. Studying these trajectories informs not only solar system science but also the potential habitability of planets throughout the galaxy. The inner solar system thus serves as a laboratory for understanding rocky planet diversity. Mercury exemplifies the effects of proximity to the star and small mass. Venus illustrates runaway greenhouse effects and the consequences of a stagnant lithosphere. Earth demonstrates balanced conditions that sustain life. Mars shows how atmospheric loss and cooling can remove habitability potential. By extrapolating these lessons, scientists predict the range of outcomes for rocky exoplanets, from barren deserts to temperate, water-rich worlds. Tidal heating drives energy in moons and influences their geologic activity. Eo's intense volcanism is powered by gravitational flexing from Jupiter and orbital resonances with Europa and Ganymede. The constant stretching generates friction within Eo's interior, melting rock and producing lava flows that reshape the surface continuously. Europa experiences milder tidal heating, maintaining a subsurface ocean beneath an ice shell. Enceladus, orbiting Saturn, displays cryovolcanic plumes where tidal flexing fractures the ice and allows water and organics to escape into space. These processes illustrate how gravitational interactions extend planetary influence to moons, creating active, energy-rich environments that may be conducive to life. Ring systems evolve over time through collisions, resonances, and interactions with moons. Saturn's rings, for example, are dynamic. Micrometeoroid impacts gradually grind particles into dust, while embedded moons and gravitational resonances produce gaps, waves, and spiral structures. The age of the rings remains debated, but evidence suggests that they are continually replenished or reshaped by these interactions. Jupiter's faint rings demonstrate similar principles on smaller scales, with dust continually supplied from impacts on inner moons. Uranus and Neptune's rings, confined by shepherd moons, illustrate that even narrow, tenuous rings are dynamically active, evolving over millions of years. Studying ring evolution informs our understanding of accretion disks, satellite formation, and planetary system dynamics. Formation theories for giant planets combine core accretion and disk instability models. In the core accretion scenario, a solid core forms first through accumulation of planetesimals. Once massive enough, it captures surrounding hydrogen and helium from the protoplanetary disk. Jupiter and Saturn likely formed this way, as indicated by their composition and presence of heavy element cores. Disk instability proposes that gravitational instabilities in the protoplanetary disk can cause rapid collapse into a gas giant, potentially explaining massive exoplanets observed close to their stars. Ice giants like Uranus and Neptune may represent intermediate outcomes, where slower gas accretion limited their hydrogen-helium envelopes. Understanding formation pathways allows scientists to predict compositions, eternal structures, and satellite systems of both solar system and exoplanetary giants. Exoplanet comparisons highlight the diversity of giant planet systems. Hot Jupiters experience extreme stellar irradiation, driving atmospheric inflation, strong winds, and chemical dissociation. Cold gas giants maintain deep convection and long-lived storms but may host moons and rings analogous to solar system giants. Superjupiters, more massive than Jupiter, demonstrate that increased gravity compresses interiors, affecting magnetic fields, heat flow, and atmospheric circulation. Mini-Neptunes, smaller ice giant-like exoplanets, exhibit variable densities and volatile compositions, bridging the gap between terrestrial planets and true gas giants. Observing these worlds allows for testing of formation and evolution models across diverse environments. Magnetospheric interactions are amplified in exoplanet systems with close-in giant planets. Stellar wind and magnetic interactions can induce auroras, atmospheric stripping, and particle acceleration. Close proximity to the host star can produce intense electromagnetic coupling, heating planetary upper atmospheres and driving atmospheric escape. Understanding magnetospheric physics in the solar system provides a template for interpreting these extreme exoplanet environments, offering insight into habitability, atmospheric retention, and magnetic field generation. Atmospheric modeling incorporates chemistry, thermodynamics, and fluid dynamics. Condensation of species such as ammonia, water, methane, and hydrogen sulfide forms cloud layers at different pressures and temperatures. Convection redistributes heat from interiors, driving zonal jets and vortices. Rotation influences the Coriolis effect, determining wind patterns and storm longevity. Radiative transfer models explain how energy from the sun and internal sources propagate through dense atmospheres. Seasonal variations, particularly in tilted ice giants like Uranus, produce long-term changes in circulation, cloud formation, and visible features. These models are essential for understanding both solar system and exoplanetary giant atmospheres. Energy transfer in giant planets is critical to storm and circulation development. Internal heat flux drives convective overturning, producing cloud formation and turbulence. Latent heat from condensing gases, particularly water and ammonia, releases energy that fuels storms. On Jupiter, this process supports the Great Red Spot and smaller vortices. Saturn's periodic storm systems demonstrate episodic energy release, generating waves that propagate around the planet. Neptune's extreme winds illustrate that even distant, cold planets with internal heat can host highly energetic atmospheres. Modeling these energetics bridges observation with physical theory, explaining the scale, duration, and intensity of weather phenomena by combining internal modeling, atmospheric dynamics, ring and satellite studies, and exoplanetary comparisons. A holistic understanding of giant planets emerges. Gas and ice giants shape their planetary systems, influence orbital stability, sculpt minor body populations, and host diverse satellite environments, some potentially habitable. Their study informs broader planetary science, from formation theories to atmospheric physics, and provides a foundation for understanding similar exoplanets. Detached objects in the outer solar system occupy extreme orbits with high perihelia and aphelia, placing them beyond significant influence from Neptune. Sedna, for instance, has a perihelion of roughly 76 O and an aphelion exceeding 900 O, completing an orbit in over 11,000 years. These distant trajectories suggest perturbations from passing stars during the Sun's early cluster phase or the presence of an unseen massive object in the outermost solar system. The study of detached objects provides clues about the Sun's birth environment, the limits of the solar system, and potential reservoirs of primordial material that remain largely unaltered since formation. The long-term dynamical stability of the Kuiper belt is shaped by a combination of planetary resonances, secular perturbations, and mutual gravitational interactions among bodies. Classical Kuiper belt objects maintain relatively stable, low eccentricity orbits, preserving early solar system conditions. Resonant populations, including the 3:2 Plutinos and 2:1 Tutinos, are stabilized by mean motion resonances with Neptune. Scattered disk objects follow more chaotic paths due to repeated gravitational encounters with Neptune, while detached objects remain in long-term stable orbits and less perturbed externally. Numerical models demonstrate that these dynamics have persisted for billions of years, allowing the Kuiper Belt to serve as a fossil record of solar system evolution. Color and albedo variations among Kuiper Belt objects reveal differences in surface composition, irradiation history, and collisional processing. Some objects display bright, icy surfaces dominated by methane or nitrogen ices, reflecting a higher albedo. Others exhibit reddish or darker coloration, indicative of organic tholins produced by long-term exposure to cosmic rays and ultraviolet radiation. Spectroscopic studies allow identification of specific ices and compounds, revealing heterogeneity even within single populations. These variations provide insight into formation location, accretion history, and surface processing, linking physical characteristics with orbital dynamics and collisional history. Cometary chemistry offers a direct window into primordial solar system material. Water ice dominates cometary nuclei, accompanied by carbon monoxide, carbon dioxide, methane, ammonia, and a wide array of complex organic molecules. Rosetta's analysis of 67P/Churyumov-Gerasimenko revealed glycine, phosphorus, and other probiotic molecules, highlighting the potential for comets to deliver ingredients for life to earlier Earth. Sublimation-driven jets expose interior materials, allowing direct observation of chemical composition, isotopic ratios, and dust-to-gas ratios. Comparing Jupiter family and low-period comets illuminates differences in formation regions and evolutionary history, providing a broader understanding of small-body chemistry across the solar system. Binary and multiple systems among Kuiper Belt objects are surprisingly common, with estimates suggesting that roughly 10–30% of large trans-Neptunian objects possess companions. Binaries exhibit a range of separations, orbital eccentricities, and mass ratios. Some systems, like Pluto-Charon, form double-planet configurations with barycenters external to the primary body. Smaller binaries and triples form through capture, rotational fission, or collisional fragmentation. These systems allow direct determination of mass, density, and internal composition, offering clues about accretion and dynamical evolution in the outer solar system. Population modeling integrates observational surveys, orbital dynamics, and collisional histories to estimate the distribution and evolution of outer solar system bodies. Models incorporate resonant populations, scattered disk objects, detached objects, centaurs, and comet sources. They predict size frequency distributions, color diversity, binary prevalence, and collisional rates, providing a statistical framework for interpreting observations and planning future missions. Comparisons between modeled and observed populations constrain theories of planetary migration, early solar system dynamics, and the influence of stellar encounters or unseen massive bodies. Volatile retention over billions of years is a critical factor in the evolution of Kuiper Belt objects and dwarf planets. Small bodies with low gravity may lose volatiles through sublimation or impact erosion, while larger bodies, such as Pluto and Eris, retain thick layers of ices and can maintain tenuous atmospheres. Seasonal cycles, axial tilt, and orbital eccentricity influence the migration of these ices, forming frost deposits, smooth plains, and transient atmospheres. Surface renewal processes, including cryovolcanism, tectonics, and impact resurfacing, maintain chemical and textural diversity, ensuring that even distant, cold objects remain geologically interesting. Collisions and impacts continue to shape small body populations. Cratering records on dwarf planets, Kuiper Belt objects, and cometary nuclei reveal both ancient bombardment and ongoing minor collisions. Impacts can trigger local sublimation, expose pristine ices, and produce secondary ejecta that contribute to dust populations. High-velocity collisions in the early solar system likely produced families of fragments, binaries, and shape-altered objects observed today. Understanding these processes allows reconstruction of accretional and collisional histories over billions of years. Exploration of the outer solar system continues to transform understanding. New Horizons provided detailed observations of Pluto and Arrokoth, revealing complex geology, contact binaries, and evidence of gentle accretion. Rosetta's long-term study of comet 67P/Churyumov-Gerasimenko co-demonstrated the chemical complexity of cometary nuclei, activity mechanisms, and the role of surface heterogeneity. Upcoming missions may target additional Kuiper Belt objects, centaurs, and comets, providing further insight into composition, structure, and dynamical evolution. Combined with telescope observations, these studies link individual object properties to population-wide processes, reconstructing the history and evolution of the outer solar system, from the fiery inner worlds to the frozen outer reaches, from rocky asteroids to icy comets. The solar system tells a story of formation, evolution, and constant motion. Each planet, moon, dwarf planet, and small body carries a record of the forces that shaped it: gravitational interactions, collisions, radioactive decay, and solar radiation. The terrestrial planets remind us of the processes of accretion, differentiation, and atmosphere formation, while the gas and ice giants demonstrate the power of gravity, internal heat, and magnetism in shaping entire planetary systems. Moons and rings illustrate the intricate dance between primary planets and their satellites, where tidal forces generate heat, drive volcanism, and sustain subsurface oceans that may harbor conditions suitable for life. The Kuiper Belt and scattered disk preserve primordial material from the solar nebula, offering insight into the conditions from which the planets formed. Comets and centaurs, on journeys that bridge the outer and inner solar system, deliver water, organics, and clues to the early chemical environment that seeded life on Earth. Asteroids, meteoroids, and near-Earth objects highlight both the fragility and resilience of planetary bodies. Impacts have shaped surfaces, influenced climates, and even altered the course of life on Earth. Understanding their composition, dynamics, and potential hazards informs planetary defense, resource utilization, and our knowledge of planetary formation processes. Through exploration and observation, humanity uncovers the connections between small bodies and planets, between distant orbits and the origins of life-essential materials. Exploration missions from Voyager and Galileo to New Horizons, Rosetta, Hayabusa, OSIRIS-REx, and beyond have transformed our understanding, revealing complexity and diversity that exceed earlier expectations. High-resolution imagery, sample returns, spectroscopic analysis, and long-term monitoring allow scientists to bridge models with reality, refining theories of planetary formation, evolution, and small-body dynamics. Observations of exoplanetary systems further expand this understanding, showing that the processes observed in our solar system are part of a broader cosmic context. Ultimately, the solar system is a dynamic, interconnected system where planets, moons, asteroids, comets, and dust interact through gravity, collisions, and radiation. Each body tells a piece of the story, from the formation of the sun and planets to the ongoing processes that shape surfaces, atmospheres, and orbits. By studying these worlds, we learn not only about their individual histories but also about the universal processes that govern planetary systems throughout the galaxy. This documentary concludes by emphasizing that every small body, giant planet, icy moon, and distant dwarf planet is part of a single narrative, a story of creation, transformation, and interconnectedness. From the heat of Mercury to the frozen plains of Pluto, from the dust of the asteroid belt to the ice of the Kuiper Belt, the solar system continues to evolve. And as we explore and understand it, we gain insight into our own origins, the potential for life beyond Earth, and the profound beauty and complexity of the cosmos.